In this video, let's take a look at how we might model a traditional cylindrical or barrel cam, in this case for a shifter. And if I rotate this part and look at it, so we have a hole through the center, some threads up here at the top, but the difficult part or the critical part then are these cam slots that are going around here. Now how to model those cam slots. And before I do that, I'm going to go to a more simple model and we'll see how to set that up. So here I have part going through here with a pin on it that would lock the pin. So either this part is stationary or the part that goes into it is stationary, and one translates and rotates at the same time. Let's look at how I set this model up. Now I'm going to bring the history tree back to the beginning or the timeline, and if I look at my first sketch, I have part of an arc. The purpose for creating that arc then is to create a sheet metal flange. Because in Fusion 360 we don't have a wrap command to wrap a profile around a cylinder, we had to model it as sheet metal, unfold the sheet metal, create our pattern, and then refold that back up. So let's look at a couple of considerations though. So this is a critical consideration. Let's inspect this arc. The length of that arc, 29.45. You need to remember that number. That's just the arc from here around over to here. Alright, and then I'm going to go to unfold my part. Now I used unfold, not flat pattern command, but unfold, and I'm going to measure that length. So I'll measure it and I see that it is now 2.615. So before, let me bring this back over here. So if I inspect just this length right here, that's the arc at now 2.615, where before we unfolded that it was 2.945. Notice it's a lot shorter now than it was when we started with. Here's what happens when you fold a sheet metal part. The material stretches on the outside of the bend and it compresses on the inside of the bend. And so Fusion is calculating that stretching, and it reduced the length of the part before the part is stretched or bent. The neutral plane, where there's neither stretching or compression, is generally not right in the middle of that thickness. It depends on the material, the thickness of the material, the bend radius, and the bend angle, and perhaps a couple other parameters that determines that stretching K factor. So if I go back to my sheet metal rules and I edit my sheet metal properties and my rules, the default K factor is 0.44. So that means the neutral plane is 0.44% of the thickness from the inside of the bend radius. In this case, we don't want this to stretch at all because we're not making a sheet metal part, but we're using sheet metal to kind of cheat and get around a limitation in functionality in Fusion 360. So I'm going to set my K factor to 1. So that would be out here, 0 would be here, but that's the minimum radius of my cylinder, and then that would be my maximum radius. Now, I don't know if you saw that, but the part just lengthened when I clicked on that. So I come back here, so I want that maximum radius, so I want the K factor out here to 1. I don't want this minimum radius, so that distance, that arc length along there is shorter than this one. This is the one I want to use, and again I measure that and it's 2.945, and I go to my unfold again after changing the K factor and I inspect that and it is 2.945. So that's a critical step in getting the rest of this to work out correctly. So the next step I do is I create my displacement diagram, and so here I have created my displacement diagram, certain distance from the edge. If I look at the dimensions, now normally we do this dimensioning in relationship to the number of degrees around the cylinder, and so we could set up a pattern of points, say 360 points for 1 point every degree along the length of that arc, so that we could then define this relative to the angle. But in this case I did it to a length to keep this this one's simple. Now when I did this, let's back up 1 minute. My thickness of my follower, or the distance of the slot from here to here, is 0.25. So I did half of that distance. Of the pin that's going to go in here is 0.25. I did half of that distance because this is the key. What I need, I really don't need this out here. I really don't need that out there. The only thing I need is the centerline travel of the tool that's going to cut this slot. So that's why I did it to just to the center line, and one side or the other side, it doesn't matter which side that we go to. And then I extrude cut that through this sheet metal part. I then refold the part back up again. Now this isn't as simple as you might think, well, I'll just extrude cut through here, and you know, that wouldn't give us this shape here. It's different. Can't just do a sweep either, a sweep of a rectangle, and I'll demonstrate why here in a couple of minutes. Let's turn off that. And then the next step is I deleted everything on that sheet metal part except for the center line. This, I don't remember now whether it was this one or this one. I guess it was this one. This was the center line of our slot. I delete everything except for the center line, and actually now I'm confused about which one that is. One thing that might be useful is to change the color properties of your geometry, the face that you want to keep. Let's go back here, and I'll go to where I've extruded cut that, and remember this was my sketch, and I'll do it on this face because this is my center line of the slot right here. So we'll go to the appearance, and I'll put this on faces, and I'll drag that to that face and to this face and to this face. Okay, so that's the center line of my slot right there. I go forward, and so I've wrapped that around. I can hide that sketch now, and I delete everything except for that center line. That's the tool path. I then extended that slightly, and you may or may not need to extend it. I extended it on both sides slightly. Sometimes you might get an error where it will leave a sliver face if you don't extend that a little bit. And then I have the sketch for my cylinder itself. So I extended that into this cylinder and out of the cylinder to make sure that I don't get any kind of errors where it doesn't completely intersect that face. Then I'll do a thicken cut of that surface body. So I thickened it mid-plane, 0.125 on either side to cut my slot. I then created a work plane at the end of this curve. I drew a sketch circle on that work plane. Let's better turn that on so we can see it. So I have the work plane created at the end of this line. I draw a circle and then extrude cut that circle to give me the end of the tool. Think of how this is manufactured. So you'll have an end mill that moves along in this direction, and the end mill just goes in a straight line. It continues in a straight line while the cylinder rotates to produce the cut. Now let's look at this in Autodesk Inventor, where I can do a little bit more explanation of what's going on. So here we have a pin, and that pin is going to go into this slot. I want to animate this to show how this works. Let's look directly at it. And in Inventor, I'm going to go to the dynamic simulation environment. And so I've set up a 3D contact between this pin and the slot in the cylinder. And the way I have this set up, the pin can only translate. It only goes in a straight line. This part will rotate. You could have it just the opposite, where this part is fixed in space and then this part translates and rotates. Anyways, let's look at it at work. So we see the pin goes into the slot and it pushes against the slot, which pushes the cylinder. I'll play that again. Now I'm going to stop this at a particular location. Now right in here someplace, let me try that again, where there is a high degree of change in the path, that is where we can have some interference, or where there should be no interference between the cutter and the path. So let's just look and see how much interference there is. So I'm going to go to the inspection tab, and I'll analyze interference. I'll select my first part, I'll select the second part, and I'll say OK. And it says that there is an interference, but let's look at how much that is saying that is. It says 6.2 e to the -7 cubic inches. So e to the -7, you would have to move this 1 and then 6 more decimal places. So essentially that's just a mathematical error that going down too many decimal places. But that interference, the major interference, would occur in here if there was any interference. Now this is where if you tried to do a sweep of a rectangle along that path, you would find more interference. So it doesn't give you the correct solution. And let's look at why that is. So I'm going to go to a section view of this, and so let's look at this, view that in half section, and we'll go back to the dynamic simulation. So notice the tangent point between this cylinder and this slot is right here at this time. I will go back to the beginning and I'll play it again. So right now the tangent point between the pin, and imagine again this is an end mill cutter that's rotating and it's cutting the slot. The tangent point is at the 6 o'clock and the 12 o'clock position as it goes down in a straight line. Then as we come up along here, notice the tangent point is here, and on the other side it would be up in here someplace. Notice that this portion of the slot doesn't even appear to be touching. It is touching, but it's way up here where it's touching. But if you did an extrude cut with a rectangle, it may come up here where there's actually a lot of interference there. And so the tangent point is changed here. It was down here, so it was as it came up here, that it was continuously variable, that tangent point moving up here, up here, up here, up here, the same way on that side where it was cutting the slot. And so I get up here, and again, when I look at it in section view, it doesn't look logical, but when we leave section view, we'll see that it is correct. This is what that cylinder is cutting. Let's reverse that section view. So I'll go back to the view tab and I'll leave section view, and I want to look at it from the other side. So I'll do a section view from this side. So I've cut away the other half of this, and again, let's follow that pin. So I'll go back to dynamic simulation, and so our tangent point is here at the 12 o'clock position, and it stays along there as long as it's a straight line. But then when it starts to curve, that tangent point changes along that cylinder. Now there's some bouncing around in here. Depends on how many calculations I do on this as well. And I can't remember whether I left a little bit of clearance in here or not. And so let's look at it again one more time without it in section view. All right, let's look at this again. So I'll go back to dynamic simulation. I'll play it again. So remember, it looked like there was a big huge gap in between the pin in section view, but it's actually because where the tangent point is located at, it's continuously variable. It is in contact, and they're both the same size, so it's in contact with both of these at the same time. I am set this up to do 1,000 calculations along that travel. The higher I set the calculations, the more precise it would be, but the slower it would be having to do all those calculations. If I just drag this, and I get this vector, this force vector. So the longer that vector is, the greater the force is that I'm putting on that pin. And if I go too fast, the computer can't keep up with the calculations. I got to be careful that I don't go too fast. And it works better if I have the computer driving it than if I try to do it by hand, or I just need to go really slow. So that it doesn't overrun the calculations. And we can display all kinds of information about that motion too, if I want to know. So here's the acceleration of the prismatic or the straight line motion of that pin. You can look at driving forces, velocities, accelerations, positions, so forth. All kinds of information that I can graph as we're playing that simulation. And actually, one of the things that we probably want to avoid, particularly if this was a high-speed mechanism, is any really sharp transition in the acceleration. You want a smooth transition for a high-speed application. So I want to look at one more thing while we're here in Inventor. And so I'm going to look at modeling this part in Inventor versus how I just demonstrated modeling it in Fusion 360. So I create my cylinder instead of a sheet metal part. I don't need a sheet metal part to do this in Inventor. I create a work plane out here tangent to the part, and then create a sketch. Let's edit that sketch. I create this sketch on this work plane, and I want to see why it's showing that it actually isn't fully constrained. I want to find out why it's not fully constrained. Okay, so I have a point in here that point still has a rotation. I was doing something earlier. Oh, there it is. This line right here, that line can still rotate. And so these arrows, when I just turned that on, showed me where that rotation was at. And I'll put a constraint on that line, and now it's fully defined. It tells me down here it's fully constrained. The degree of freedom arrows turned off, and then I wrap that around this curve. And actually, so this was my pin that I used to cut this with. Here's my 2D sketch, and then I wanted to wrap that around the cylinder. So in the 3D sketch, I selected project to a surface. I selected the face I want to project to. I want to wrap that to that surface, and I select the curves that I want to wrap to it. And so whatever my displacement diagram is, I can wrap it around the cylinder instead of doing a sheet metal fold unfold like we did in Fusion 360. And then once I have a path, I can tell this cutter to go along that path and cut my part. I'll do that now. I tell it to take that cutter and take it along that path and cut out my part. So here's my Fusion 360 part, the more complex part, and I'm going to send my timeline back to the beginning. I'll go forward one step. I created a work plane half the distance of the cylinder from the origin plane, and then on that plane I put a canvas or a scanned image of the displacement diagram. So this was an image taken from actual part, and I'm going to edit this image. And so I'll right click and say calibrate, and then I need to select 2 points on this. So this is a hole in the part, and then this is the same hole after having gone all the way around the part. And there are other locations where you could find the same sort of thing. So this point right here is the same as that point right there. So I'm going to click in the center of this circle, and I'll click in the center of this circle, and right now it tells me that image is 13.763405, but I know the actual distance is the diameter 41, that's the diameter of the cylinder, times pi will give me the circumference of the cylinder. And so I'll press enter on that, and that rescales my image. So now my image is 1:1 scale. I might want to make some other changes on this, so I'm going to edit canvas, and I'm going to make that darker so that we can see that better. I may want to move this so that the origin is in a particular location. I might have made that too dark where I can't see the origin. If I want to move this, I can drag this and move that, say maybe I want the origin right there or wherever. So I put the origin in some particular location, and then I may need to rotate this one way or another, and I can also tell it that I need to flip horizontal or flip vertical if I need to. Let's say we have it mirrored backwards or something. Anyways, once I get that done, I then create a new sketch and I lay out the distances for my displacement. So I create a displacement diagram, and I guess I can start to do part of that. I've already done this, and so I have it all laid out, so I'm only going to do a portion of it. But I have a line, you know, a straight line from here to here, and then it's going to go in a curve and so forth. You could dimension these lines, and to get our displacement diagram, don't take the image too seriously. So hopefully you have a physical part that you can go back and forth with your measurements between the physical part and the image, because it's hard to tell from an image. You're going to always have parallax error, some errors that make it difficult to to use the image. So anyways, I went through that process and created a displacement diagram. I'm going to turn that off for now. So I'll turn off the canvas, and I'll turn off work plane, and I'll turn off the visibility of that sketch, or I might just delete that last sketch. Alright, so the next step I do then is I create the sketch for my sheet metal part like I did on the original. But I had to do this in a particular way. A sheet metal part has to have a straight section to that sheet metal part. And so I've got a straight section going from here over to here, and then I have the curve that I'm going to lay out my slots on, or at least a couple of the slots. So then I create the sheet metal part, and so let's go up here to our solid bodies. And so here's our sheet metal part, and the thickness of my sheet metal I have set to the depth of my slot. So if I go to sheet metal and I set this to the rules, I see that I have it 4.5 millimeters, so my slot I'm going to put is 4.5 millimeters. If I edit this, I have the K factor set to 1, so that's an important step. Alright, then I unfold that portion of the cylinder where the slot is going to be. I then create a sketch for my displacement of my first slot. And remember, one side of this will be the center line, so I only go half the distance. And let's just look at the dimensions on that for a minute. So I'll do show dimension. So the thickness on this 3.03, so my total slot width is going to be 6.06. And any of these dimensions now can be changed. So once we create a parametric model, we can lengthen the slot, we can change the radius of the arc, we can edit this slot however we need to edit it. And then I do an extrude cut just like I did on the first problem, and then refold it, then delete everything except for the surface that is my centerline surface. And then I create a new sketch for the next path. So again, I use that same technique of part of a straight line and the curve that will encompass that path. I go a little bit beyond that, so I have some extra material. And then I do my sheet metal flange again. I unfold that, and actually I split this face up here from this point on the original cam so that I have the same reference point on the cam. I projected this point up, split that face, and then when I unfold it, I have a reference point here that I can use that references the same point on my first flat pattern. And then do the sketch, and then do the extrude cut. Then to the next step, I did this one down here, so these two profiles start and end in the same place. So I have those two sketches connected together with construction lines, and I guess I could have done both of these in the same sketch and then just one extrusion, one extrude cut, but for editing purposes it may make it easier to not have too many dimensions on the screen at once, and so I did it as two separate sketches and two separate extrusions. I then refold my model, and this is the second sheet metal body now. I'll delete everything except for the center line of the first side. Let's back that up. So I have two slots in this now, so I need the center line of one of these. This is the center line of the first slot that we did, and then I need the center line for this slot, the center line for that slot, and so I get the second one. Actually, I think I already have the third one. They just don't have it visible. Yeah, there's the third one up there. Okay, so when I did that delete, I deleted all the faces except for the center line for this one, the center line for that one. Then I sketch my circle for my cylinder that I'm going to cut these out of, and I copied these surfaces. We'll see why in a few minutes, but I have a copy of each one of these surfaces offset distance 0. Okay, so I offset each one of these surfaces a different distance 0 to give me a copy of those surfaces. And originally I didn't think I had to do this. I don't recall why I ended up doing that. Oh, well, I know why I did it, but I don't think I should have had to, and I don't think I had it in there originally. And then I extrude cut one of those surfaces, you know, this surface, and then I I do thicken. That's the key. You do thicken mid-plane, the thickness of your slot, thicken mid-plane, the thickness of your slot. The machining purposes, you're going to want this curve right here to define the path of your cutting tool, and so that's why I put these copied offset surfaces at distance 0 in here, so that those could be used later when generating a CNC code in the cam. Right, then in the next step, I put the top and bottom of the hub, and I could have put those in originally before as part of that original extrusion here, and then put a fillet in here, did a work plane here someplace, and we'll look at that work plane. Notice all of my sketches are fully defined. So I created a circle. The cylinder is rotating as it is being cut. When it gets to that last spot, it actually leaves a little bit of a flat there. Half of this will end up being a planar surface. So I do an extrude cut so that there's a planar face right there because the rotation stopped. And the same way at each end of this. So I did the same thing at each end of this slot. And so I have that one and have wherever the next one is here, and this one and this one. Again, there's a planar face right there, planar face right there, right there. It's not cylindrical like this face because the cutter stopped there, or the drum stopped rotating as the cutter was cutting the slot. And then continue cutting away from my piece of stock. Put my hole in here, a threaded hole. Put some chamfers on here. There's a large chamfer, small chamfer, some fillets, a chamfer on the threaded hole, the hole cutting through the side here, and the hole cutting through this side right here. So that is cutting cam slots or cylindrical slots in Fusion 360 using a trick with the sheet metal tools. I'll take a look at briefly how I did part of this in Inventor, and so I'm going to go up to my first sketch. And so if I turn on the visibility of the sketch, so here is the centerline path of my 3 slots. I'm going to turn on the visibility of the original image. So here was the image used to lay out those paths. Let me turn that off again. And then do a wrap of the 2D sketch around the part to get the paths as they go around the cylinder. And then you can go and continue to finish the rest of the cam. I'll turn off the visibility of my 3D sketch. One final thought on the design of cams. So normally when we're laying out a cylindrical cam like this, we specify the slot in terms of the angle going around the cam. And so for this distance, I have it calculated as 41 millimeters. That's the diameter of the cam times pi. That gives me the circumference times the angle I want out of a total of 360 degrees going around the cam. And that converts that angle into a linear dimension that we can then wrap around the cylinder. And then if we're using a cam generation tool like the Autodesk Inventor cam generator, we set our angles that we want and what motion we want to occur in between the angles. We can put in the radius of the cam, the depth of the slot that we want, all of the information that we will use to generate the cam itself, and just specify the lift over certain displacement. And perhaps all we want to do is look at just the graph of just the lift. We might also want the acceleration curve, and we want to probably avoid sharp changes in acceleration like that. And we can specify the motion laws where it changes from, say, a linear motion to a harmonic motion in between the various segments of the cam.